the language function. See how you can write it. And you will write it as adopting high strength string. No, but not for this one.
No.
Oh, you can get my.
Get some water.
Yeah.
So it's not this one.
Huh?
It's not this one.
No, it doesn't require. I think you and Gaia both apply. And see if you can get it, increasing the chances. Okay.
I just want to ask we just need a password for the DAC computer thing because the thing that the coupon we tested today. I just need a photo of it.
No, I have to be with you actually. I will have to come with you
Okay,
as well. Whenever I have time, because I know I don't want to give the password.
Yeah, that's okay, that's okay. Whenever you will be free.
Yeah, maybe after we end this workshop, right?
In about 2 weeks.
Yeah, around 1, 2, something like that. Yeah.
I just need 15 minutes whenever you're free.
Yeah, sure, we can. You have my number?
I can get it.
Yeah, get it from. Yeah, I don't have. I can message, or you can just put me your number. Yeah, I can message you my number.
Okay.
Sorry, you are saying?
Type your number so I can. You have my number.
No.
Thank you.
Yeah, sure. Yeah, sure. Just put my name here, so you know that it's my number. Okay, thank you.
Okay. Yeah. We will start working on something. When we will plan for your what next we will community. We will try to meet go through your one of the yeah, tomorrow.
So you're recording it, right?
It is live stream.
It is live streaming now. I better watch out what I say.
Yeah.
No, but yesterday, so you were live streaming too?
Yeah, but live stream is at the end. It's recorded, so you can.
But those must be really big files.
Yeah, I was telling Dr. Alam it's better to do that through YouTube directly, so you can even control the quality, whatever you want to do it. Because if we do it with a regular cameras and tripods, it will take like 1 day to upload it.
Yeah, that's
and
what I'm saying. Like 6 hours. That's just gonna be a huge video file.
And this cameras is very like with storage we have is like 64 gigs or something.
Yeah.
So you will take like processing for these videos a lot of time.
Yeah.
But YouTube is handling all that for
Just
free.
easily,
Yeah. And hopefully if our channel get more people interested, we can get money as well.
Yeah.
Yeah, YouTube, people makes but there's not this kind of videos, but they make millions.
Look at mindless videos, you know?
You are doing it to Alliance?
No, I like it has to be through the Facebook page, but you have to validate your YouTube channel personally. So they have to. So I have it on my Gmail account, but I'm getting everything there.
Yeah, like you can get the money, no? So, like,
Yeah.
you should through the other.
No, I mean
Yeah, you can create.
another email. Yeah, we can do another one.
Yeah.
We have that one that we use with LinkedIn.
Yeah, use that one.
Yeah.
Do everything from through there.
Okay, I will.
You have to. Yeah.
To maintain that one. Yeah, I
Oh,
already
okay.
have that one, but by the time we started,
Yeah. So it's better to maybe later on you can, I don't know, you can
transfer. Yeah, you can just download these videos and transfer them, then start from there.
Downloading is very.
No, but from YouTube, I guess it will be easier, like to move this from here to there.
Okay. Like next time, you try to create
that one for the next test setup.
Yeah.
Yeah, sure. So, shall we start? It's 9:15.
So we're waiting for a few other people, or?
Yeah, these guys, I don't know why they are late.
We can wait for a minute.
Okay, so let's wait for
Yeah, we
5
can
minutes.
make for 5 minutes. Saf, when is your comprehensive coming up?
He was just telling me, like, should be by the end of this year, basically.
So you and I are probably going to be doing it, like mine is January.
Yeah, maybe we'll go schedule it in January. We'll end up in January.
Mine's already scheduled for a week.
Oh, in January,
Yeah. Are you're a take home too?
Yeah, I think it's going to be taken forever.
Unless the plan want to change, but I guess.
Yeah, I think.
And are you getting a week too, or what are you getting?
I think it depends on the advisors.
The committee.
Yeah, in case of Marian, they're going to give it 1 month because of the questions.
What are they asking for a whole month? Like it's more of a project then.
Yeah. Apparently one of the guys, he's part of my committee as well.
Okay.
The same professor who's asking.
Who is this? Who's this professor?
He's a finite element guy.
This is Dr. Milania. That's Milania.
He likes the brick element, the one he hates.
I hate.
He's a brick element guy.
Bridges, the brick element does nothing for
It
us.
doesn't work, yeah. Unless in research, like some people do.
What's that?
Like unless you're doing research, some people.
Yeah, but even then, like, it's got to be very, very targeted on a very small component of
it.
the
Take forever to run the model. Yeah.
That's what I was saying to Dr. Disney back there, that UBC Vancouver has always had a very regimented thing. It's very streamlined. It's a week. Everybody gets a week, a take home, and that's it.
So it's becoming like uniform.
Over there, it's always been that, but then you were saying that it's changing now.
Yeah.
They just changed the policy.
Oh, they changed the policy.
Before it was oral, now
Yeah, but UBC Vancouver never had an oral.
So
It was always 7 days written. Then you had to go and defend it. In, what's that?
Yeah, they did
They
have
did?
an oral, and then now they changed to the written.
Everyone that I've known over the last 2 decades at UBC Vancouver, they've had to they've had to take a written exam for 7 days, and then gone back and defended it orally, and then of course the proposal defense is separate.
But this kind of oral one came up quite recently, maybe less than 5 years ago, and then now they changed it back again.
Oh, okay,
Yes.
okay. So that might have.
just for testing the ability of the student to do research.
Yes.
Their own research. And
Yes.
In oral presentation, they want to see how spontaneous the student is going to react to unexpected questions. So they want to see the flow of critical thinking in the student. So that's the main purpose of this.
Right.
To be so sure that this student is capable to continue with the research.
Right. Yeah. And that makes
That's
sense.
the main. That's the main. Because most of the questions are open-ended.
Yes.
There's no quite
No real
specific answer.
answer, yes.
You have to dig and you have to find the best that you can find. And for sure, for let's say for 1 week, that would be impossible to give a comprehensive.
like a very
You can put your idea. You can put
Yeah.
basic. So that's the essence. They are not. They just want to focus on that part. We all tend to accept all the student rather than paycheck.
yeah.
Because that's the past.
Unless somebody's really, you can
Yeah,
see that they're,
It's a pass grade exam. It's
Yeah.
not
Yeah.
objective.
yes, it's not.
It's a 65% rate. Like, you should grade for
Yeah, I understand, but that's something,
Yeah, I mean-
something qualification.
Yeah, qualification.
Evaluation.
The most challenging part is to get the questions and get the signature. This is the most challenging part. To get the question, like you could spend like 1 month from the committee to get the questions
Right.
in an open loop, and you don't know like how to catch the question.
Right.
And after that, to get the signature, if you pass these 2 stages, then you can be very easy one.
Yeah.
Yes. The far ends are the
When you get the work, you can do the work. It's just
Yeah.
getting the work.
What do you like to get the signature?
They will say, like in my case, it told me I have to do my annual report, so we go into we mark that I have passed the comprehensive. So I keep pushing them after submitting that exam that shall I mark that one? Please let me know if I have it. Then they all confirm that okay, you can mark that one that you passed the comprehensive exam. And I did submit my annual progress report. As I passed it, they already have a written email that yeah, you can mark that with their signature on. But later on, I knew from channel that this is not sufficient. There is a form that it has to be signed.
They have to sign it.
Yeah, that you have passed the comprehensive. I have been struggling 2 months now to get this form signed.
Yeah.
Like,
Because they signed this form, then you don't have to do a comprehensive, I guess.
no, they said through the they told me that they have marked my exam, and yeah, you can mark that you passed the comprehensive exam, but where in the annual progress report. Now there is a separate form. It's just the documentation. A separate form that you have taught the comprehensive exam, which is
all the committee.
all the committee members and left at the School of Grand Studies, which means the same. But they are not objecting, but to catch them,
Okay. So
Yeah, I think we can start. It's like me and Diane, we have to get out for a meeting
yeah.
at 9:55. But we
Okay.
I think.
Okay. Okay. So welcome back. Just before we go, any questions so far? We've touched on a lot of things yesterday. I have a bit more on the pushover side of things before we go and touch a little bit on the nonlinear time history. But as I was saying yesterday, if you can do a response spectrum analysis and run a pushover in a meaningful manner, then you've basically won half the battle. You just need to understand what these two things are all about and how to use these to explicitly demonstrate your performance. I'll show you a couple of examples later of how we go down the strains. So we'll have some discussion around that. But any questions or thoughts, comments so far? Anyone might have? Okay. So when we finished yesterday, I said I'll show you a little hand method to basically get you to that total base shear, just to check if your program is making sense or not. So this is a very simple example. You have a 2-column bend. It's 72 or 7.2 meters clear height. Then there's a 1.8 meter deep cap beam. And so that's why you have that 900 mils of a rigid offset. And then that 3 meter offset is to get you to the CG of the superstructure. And that's where your shear force is applied. And I've basically taken some numbers. There's about an 8,000 kilonewton of dead load on each one of the columns. Now, of course, you would have done your your moment curvature analysis separately or your PM analysis separately. So you need to know what your plastic hinging moment is, okay? So just going back to what we were doing yesterday, when I form all four hinges on the two columns, I've got an MP here, a plastic moment. I've got a plastic moment everywhere, right? I've formed all four hinges. That's where we start. So if I look at one column, that's my shear in each column. And the same is happening on the other side. So we had come up based on this free body diagram with this formula. The V is 2 MPs divided by the L. And that's where we're starting in this problem. We're basically saying that corresponding to an 8,000 kilonewton axial load, the plastic hinging moment in the column is 5,300 kilonewton meters. So I can start here and I can say, okay, both columns are going to form two hinges, one at the top and one at the bottom. This is my first iteration. Of course, it's not correct that they're forming the hinges at the same time, because as you're moving, we know one column gets lighter, one column gets heavier. It doesn't quite work that way, but we start with an assumption. So my MP for 8,000 kilonewtons is 5,300. So for each column, I get about 1,450 kilonewtons of shear. And I multiply that by 2 because I have two columns. I get 2,900 kilonewtons of shear in my vent. Okay, so if I have a total shear of 2,890 kilonewtons, and I'm pushing on it with this V value, you can imagine that this column is going to get heavier and this column is going to get lighter. How does that shear get resisted? It can be resisted by an equal and opposite couple due to the axial load in the column. So now I'm going to calculate that. So if I go back here, the lever arm to the base from the V is this 8 meters plus 3 meters. So that's the moment, 28 times that lever arm, and that's resisted by the couple of the axial loads down here, which are 7.2 meters apart. So the axial load is simply obtained by the moment divided by the lever arm, and you get plus minus 4,500 kilonewtons. Okay, so now I can say that my leading column is getting heavier by this amount, 4,460, and this is getting lighter by 4,460. Okay, so for the second iteration, I can add that to my original load for the leading column and subtract for the trailing column. So the leading column all of a sudden becomes 12,000 kilonewtons heavy, and the trailing column is now lighter. It's at 3,500 instead of 8,000. And of course, I will have corresponding to those, I need to know my MPs. And that's why I was saying you need to have your PM chart figured out first. Now my calculation is different for each column. It's the same way I've done it before. So instead of the 5,300 or whatever I had before, now for the left column, the trailing column, I use 37. For the front column, I use the different value, 5,200. Now you can see my shears are different. And my total shear has come down to 2,475 instead of 2,890. Okay. I compare that to my previous run, and I find that the base shear is the difference is about 14%. So we're going to go one more iteration and see what happens. Now my shear is 2,475. I do the same thing, and my axial load changes plus minus 3,890. So with iteration number 3, I add this much to my leading column, whatever I had before, and I subtract for the trailing column. And my axial loads change again, my plastic shears are going to change, and I get the left and the right. And my total shear now is 2545, which when I compare to my previous one is within 3%. So I've basically converged. Okay, so when I look at this, the difference between the previous iteration and this final iteration is 3%. I don't think we need to go any further because this is really a check on your software. This is just making sure that you're getting in the ballpark. And then when I compare this value that I've got here with SAP, I'm within 5%. Okay, so you could do one more iteration and say, oh, now I'm at 0.5% difference, but big whoopity-doo, right? And then I get something that's very close. So you can start with whatever dead load, axial load there is. You can come up with your initial shear force and come up with the difference in the axial load. Now you change the axial load in each one of the columns. Their plastic moment capacities are going to change. You come up with shears in each column separately, add them together, and you compare that total shear force with whatever your starting point was. Most probably in the second iteration, there is going to be a significant difference. Then you go back again, do the same thing by the third or fourth iteration, you'll converge to where it needs to be. So that's just one way of again making sure that we don't go down that trap of here's the software and we don't understand what it's doing. Now once you've done this many times, after you've researched for 5 years or you've been in the industry for 5 years and you've done lots of pushovers, you start to develop a because with computers, they're a great tool, but they're as dumb as we are. I mean, a computer is as sophisticated as the person who's making the input until AI comes to that point where it just completely takes us over. That's a different problem to be had. So this is just again, I think I just threw it in there just to remind us of the fact that while we're doing all of this, we need to be aware of brittle shear failure modes. So this is just showing a decrease in your shear. So when you have your curvature ductility of 1, which means you haven't really formed a hinge, you've got the maximum shear capacity in concrete. You can, with this work, you can go all the way up to 3 if you have uniaxial loading or unidirectional loading. But when you're bidirectional, it's worse. As soon as you start to go plastic, this starts to drop. And then out there somewhere, it drops to its minimum. That's for columns, this is for beams. So when you're doing research or somebody's planning your testing protocols, and you know that you're going to cycle it back and forth and it's going to have this degradation, just make sure that you run some sort of a calculation along these lines, have some idea of what ductility it's going to see, and make sure that you put enough. If you're testing it for flexure, just make sure that you've got enough in there so that you won't have a premature shear failure, because then your test is going to be just a bit of a waste. Okay, so just make sure that you're aware of the fact that shear capacity is going to degrade with cycling back and forth. Our code also has a formula which is very conservative, I think. That's being changed in the new code. So when you're designing these your specimens for testing, look at the code, look at maybe Priestley's work, look at other formulas where you're accounting for this shear degradation before you go and push it too far. Okay, this is going to help us. I think you guys would probably already know this, but for lump plasticity models, we kind of fudge things. Okay, so this is in reality what happens. You've got your yielding, your plasticity is not happening at a single point. It has a finite length, and that's the plastic end zone. Is what we call it. The plastic hinge is a mathematical construct. The plastic hinge and the equivalent plastic hinge length, this LP, is a little bit different than the zone over which the plasticity is spread. That plastic hinge length is just to give you a length so that your top the displacement at the top is going to match your experimental results. Okay, so when you look at the Priestley equations or other equations, it's not that your plastic hinge length is equal to where your plastic curvatures are happening. It's a little bit different. It's just back calculated. So in this case, you can see the curvatures are not linear. They come down and then they jump, and there's a little bit of a change as well. When you convert this curvature, so this is your yield curvature, that's your plastic curvature, that's your ultimate, then you can convert that into this force displacement curve where you have delta y and delta u. So that's what happens in a single curvature column with a column and double curvature. You form the same thing up and down. So you see this is the actual curvature, and you can pretty much see that it's changing, right? The LP value is going to be a little bit different than the distance over which the actual plasticity is spread. And that's why the fiber models capture things a little bit better. However, they're computationally a lot more expensive. And again, when you're trying to understand things a little bit, I think there's no harm, especially in research, in going to fiber models. I think they give you good results, but it doesn't hurt to do a little bit of a lump plasticity model and kind of see if there is a correlation, if you're getting similar numbers from using a lump plasticity model versus a, a spread plasticity model. The actual term will come to me, I just made that up. Okay, so I think we went through this. I went through this yesterday on the board. You've got the 4 hinges, and then you've got the earthquake versus the ultimate. And as long as your earthquake displacement occurs before your failure point, you're okay. You've met that target. So this is just giving you the wording for what I described for about a half hour yesterday. So Priestley. Dr. Priestley came up with this equation. Hopefully everybody has seen it. This is for an equivalent plastic hinge length that we use. So now let's talk about how we're going to use some of these results. And I'm just going to cook up some numbers that hopefully will make some sense to you guys. If I look at the moment curvature analysis, so this is my cracking moment, this is my initial yield, I go through here, this is my effective yield, and that's my ultimate. And so I have my effective yield moment, my initial, curvature, and then here is my ultimate curvature. Okay? So we saw what was happening in our software yesterday. When we pushed it, yes?
How to determine what is the effective yield strain or curvature or moment? Because you said that for the rectangle it is easy to know because it is all the parts will be together. But for the circular section, the first bar will be added, but the remaining bar will not be added. So how to know now it is the end point?
Yes, so you're asking how we come up with this effective yield point.
And the yield one, you mentioned that in case you have a circular and they are not yielding at the same time. So it is the first yield.
Yeah, so that's what I'm going to. I get the question. question, so let me answer that. So there are different ways of doing it. I've seen different ways of doing it. It's a mathematical thing, how you want to define it, okay? What I have seen done are two things. One is, so basically it's this point that we're after, okay? You're gonna draw a line, and this is how extract does it. You're gonna draw a line from your origin point, and you're gonna make it go through this initial gear point. Okay, now the question is, how far up do I extend it? And it works with energy. It works with equal areas. So this is obviously not drawn exactly how I intend to draw it, but what it does is it takes this area, which is under this red line and blue line, where the red line is higher than the blue line, and tries to make it equal to this area. That's how it bilinearizes it. Okay? I've also seen in some cases that you have this phi and you go up to about 5. It doesn't go up like that. It just stays somewhere around here along this line. So you go to a multiple of initial gear and the curvature side, and you say that that's the point. That's how I've seen it being bilinearized. I don't think that the error that you're going to accumulate is too much. It's the principle of consistent crudeness. It's you're using a lump plasticity model that has some built-in crudeness and assumptions, and then you're doing this. But I think this is not a bad way to bilinearize it, and that's how a lot of the softwares do it. They try to make this area equal to this area.
So,
yes?
Get the first part of the question, the phi yield will be at the starting yield of the extreme fiber in case not all the bars reach the yield at the same time.
So initial yield is where your first rebar is yielding. This point here is your first rebar yielding, whether it's a rectangular column or a circular column. And that's why now you won't see a lot of this in a rectangular column because all the bars are very, even if it has got 2 layers, the 2 layers are very close to each other. So they yield very close to each other, right? So you don't tend to see a lot of this rounding off. You see up, well, cracking, shift, and then it kind of goes flat, right? So that's much easier. It's usually with the circular column where you have your rebar centroids are changing a lot is when you have to do this sort of thing. Okay, so what I want to point to you is that there are 2 distinct portions here that you can think of. One is the yield curvature, and the other is the plastic curvature. Okay? So how do we use what we get from the software? So just stay with me for a second here. Here's I'm going to explain it here because if I read it, nobody's going to get it. So don't worry about what's on the board. I'll explain it here, and I'll give you those, and you can read it on your own time. So now here's my pushover curve. And let's say this is my delta earthquake. These are my 4 hinges. This is my F. This is my delta. These are my 4 hinges. So I've just drawn the force displacement curve here. Okay? And I find out that my delta earthquake, whatever return period I'm targeting, let's say 2475, is sitting there in terms of displacement. Okay, good. I go into my software. I showed you that yesterday. It had several steps. It had lots of steps. And let's say that this point is at 75 mils. Just for example, I go into my software. I figure out at what step of my pushover my bend has been pushed to 75 mils. Let's say that's step number 35, for example. Okay? So I will go into my software, and at step number 35, I will get the plastic rotation for each one of these hinges. Okay, so the program, what I was showing you yesterday, it gives me a theta p value. Hopefully everybody remembers that. It gives me that plastic rotation. And I can get it for each one of the 4 hinges. And that's where I would start. After you've done it for a while, you start to develop a feel for, okay, which hinge is going to have more plasticity accumulated, okay? But even here, you can see that the first one is more likely to have a larger plastic rotation because it hinges before everything else. The only issue is the axial load in each hinge is different, and the moment curvature curve for each axial load is different. So the strain corresponding to a given rotation for an axial load is going to be different in each one of them. So it's good to check all 4 of them. But let's say that we figured out that it's the first hinge that's the most critical, okay, and it's going to have the most strain. So what do? At that point, so let's say that this is that first hinge. And I've got a theta p value for it at step number 35. So far, the story makes sense? Somewhat? Yes? No? Okay. So I'm going to, I've figured out that at 75 mils of deformation, which is my response spectrum analysis number, my pushover gets to that point at step number 35, and the first hinge is going to be critical, okay? What I do is, I go into the program, I read the theta p value at that step for that hinge. Corresponding to that, I have my P and M. At that point, you can also read your P and M, okay? So now you go into that, you'll use the moment curvature graph for that P value. And here you'll have the M happening at different points. So what I'm going to do is, my curvature, phi P, is simply theta P over the equivalent plastic hinge length. That's what I've written here. Okay, so what am I calculating here? I'm calculating this bit, phi P. How am I calculating it? By getting the plastic rotation from the software, dividing it by LP using an expression like this. Okay, because it's been calibrated. So now I know what my phi P is for that step. Okay? I know the phi P, and I know at that step what the P value is at this, for this column, for this location. Now I go into the moment curvature graph for that P value that I've gotten out of the program. And I know what the I've got my plastic curvature. So in this graph here, I can read the phi y, right? From the moment curvature graph, I get the phi y. All right, so this I can get from the moment curvature graph. When I add the two together, I get my ultimate curvature, which is phi y plus phi plastic. So again, I get the plastic rotation from the program, I get the P value from the program. I divide the plastic rotation by the plastic hinge length, I get my plastic curvature. Knowing the P and the M, I go into the moment curvature graph, and I can read the yield curvature. I add the yield curvature to the plastic curvature to get my ultimate curvature. Now, in Extract or other softwares, it'll tell you for a given curvature what the strain values are in your different materials. So this then can be tied to ECC, and yes, I was showing you this yesterday as an output from extract, where I showed you that little bit of a fuzzy table. Now I compare this and this to my limits. So let's say that I have extensive damage. This needs to be less than 0.05, and this needs to be less than 0.8 of the ultimate. I know what my Manders confined ultimate strain is. I know the steel is 0.05. The program gives me those values. So I compare those values with these limits at that step, and if they're lower, my performance has been satisfied. Yes?
But should we call it curvature at demand or curvature at ultimate? Because it's at demand.
So this one is the ultimate curvature.
Yeah.
The curvature that is going to correspond to this step,
It's the curvature at demand.
that's the curvature demand, and that might sit here.
Yeah.
So you could also, if you work backwards from the strain side of things, you go into your table and you say, oh, my 0.05 is happening at this curvature, or my 0.8 ECU is happening at this curvature, whichever one is lower, that becomes your curvature capacity, right? So then you can just compare curvature to curvature. It's the same thing, right? So you have to figure out the strain curvature correspondence, then you can compare either curvature to curvature or strain to the strain limit. Because you're doing the same thing, right? But essentially what I'm trying to get across is, with a lump plasticity model, how everything comes together. You run your response spectral analysis, you get your lower displacement demand, you run your pushover, and you impose your displacement demand on that. You figure out from your pushover where that displacement demand sits. At that point, you figure out your plastic rotation. You divide that by the plastic hinge length to get your plastic curvature. The p-value and the m-value lets you go into the specific moment curvature graph. When you're in that moment curvature graph, you can figure out the phi, and this is your total, right? So you could think of this as something that corresponds to 0.8 or 0.05, or this could be the ultimate. But if you are trying to satisfy an intermediate state, not life safety, then you got to figure out that curvature. So you can compare that curvature to this curvature, or you can take this curvature, go into your program and figure out the strains, and then see if they're lower than those strains. And if that is the case, then you have satisfied the performance for that particular case. So all of that is kind of given in here. And this is, again, if you're comparing curvatures, I'm saying if your earthquake curvature is less than your ultimate, then the design is adequate. So take your pick, whichever way you want to go. At the end of the day, it's the same thing. We have some other expressions. ADC32 has those, and Priestley is a little bit different. So Priestley goes with the diameter of the longitudinal rebar times 0.022 times the effective yield. And if that value is less than 0.044 times the yield strength times the diameter of longitudinal rebar, then that governs. This is your minimum. Okay, I want to touch a little bit on degradation and second order effects in a pushover analysis. Sometimes we have to do that. Not a whole lot of the times, because we have in bridge columns, they're usually not very slender. Sometimes you do see slender columns, but if you see slender columns and you're worried about second order effects, you might want to turn on your geometric nonlinearity in the software. So we'll talk a little bit about. I've already talked about that plastic hinge output utilization. That's what we do with it. We divide it into all this stuff. So I've already described that. So we'll launch into pushover, including P delta effects and hinge degradation, etc. And I want to talk a little bit about some specific applications and pitfalls, which will really be a recap of what we've talked about so far. Okay, so this is done with numbers, what I was just describing. So I've given you some numbers here in terms of this is the height of the column. So here's your LP, which one of those governs, and so on and so forth. So you can go through this with actual numbers, and then you can figure out what's going on. You can also, I'm not going to go through this in any kind of real detail, but you can come up with the post-elastic stiffness for your hinge, and that again is from your moment curvature analysis. All it is coming up with the slope of this line and comparing that to the slope of this line. Okay, so basically you take that moment minus this moment divided by the yield curvature, that gives you the EI for the post-elastic branch. Oh, and you know the EI of this branch. If in the software you want to fudge it relative to this, that's the ratio that you want to put in there. And that's all just given here. Okay, so let's take a real world example that I worked on. I was doing an independent sort of a review on this structure. It's in the it's close to Tawasan. There's that other when you go to the ferries, it's just off to towards the port side, and this is a bridge in there. It's part of the Vancouver Fraser Port Authority, and here you can see the columns are very slender, and there was a reason for that. It was a bit of a we had to think about it quite a bit, and the reason for the columns being so slender was the fact that the soils here were quite poor, and we were rather limited in terms of the type of piles we could put in. So the piles could not be very big. And in order to keep the piles capacity protected and not throw too much demand in there, we could not make the columns too big. So the columns had to be slender because the piles could not be very large. I forget the reason exactly why the piles could be that big, but we had to go with Frankie piles there, which are not, they don't have a lot of lateral capacity. They're good, but we had to work with those parameters. So this is what happens in real world. Something starts to drive your design, and then you have to think about coming up with something that's going to work within those parameters.
What's the width of it? How long is that?
The width of this this thing? I think this is about about 15 or so meters.
Couldn't you put a cap on it and then the columns go on it so the road
This thing? Yeah, this is a big cap,
So then
and you have these Frankie piles.
the columns,
Yeah,
the road comes into that cap, then it's distributed and goes into the.
but ultimately it goes into the piles. You couldn't put a spread footing there. The soils.
It wouldn't make a difference if the columns were big because still the road would go into the cap, then goes into the. It's not a point road, right?
No, when you push on it, the piles go into bending. So under lateral loading, the piles are in bending and shear plus axial load. But these piles are primarily going to go into bending.
I think she's talking about the columns, like how is the soil is affecting the slenderness of the columns, yeah?
Because you said because of the piles, we couldn't go with big columns.
Yeah.
I don't understand that because if there's a cap in the middle,
Yeah.
then it wouldn't matter what size the columns are.
No, if so, the cap just acts as a rigid body. This cap,
Exactly.
it just acts as a rigid body. It throws all the load into the piles. So whatever shears and bending moments you're generating here So think about the base shear that's coming through. All of that has to be resisted by the piles. So if these columns are bigger, and now you think of capacity design, if they're bigger columns, their MP or their overstrength moments are going to be much larger than columns that are slender. So if the columns are bigger, their capacity is going to be higher. So the overall base shear that you're going to see is going to be larger.
Because using big numbers, like if you use 4 big columns, you're going to use 7, for example, small columns, right?
Yes.
So still the sum of the base shear, I don't think would be any different.
No, we looked at the column configuration. If you use big columns and you start to take these out, then your cap starts to become very large because it's got to span a longer way because now you've also got the live load on it, right? Okay, so this was done in stages, but that's okay. This is the model that I want to talk about for a minute. So you've got the columns. This is just shell elements, just to give that. We're not trying to get anything out of these shell columns. That's just mass concrete. And then you have the piles with nonlinear springs, which we call PY springs. So this is the behavior of your soil. These things are known as PY curves. And that's really to look at the soil structure interaction. So what you'll see is at every point, there is a spring attached. This point is fixed in space, and then there is a two-noded spring that attaches that point at this point, and within that spring, we input this whole nonlinear graph. But because the pushover is a nonlinear analysis, now we don't need to do the iterations. The program itself is going to find, as you're pushing on it, where something is sitting. Okay. So you can see we've modeled them at up and down. These were modeled at about a 1 meter interval, and they're acting in both directions, longitudinal and transverse. Plus, for skin friction, we model the vertical component. And we also have, if you have bearing at the tip, there's a vertical spring at the base. Yes?
And in particular, we will use shell element for the pile care.
It's just mass concrete that's huge. So we just wanted to make sure that we had rigid stiffness there. You could put lots of stick elements. That's just easy because we're just trying to get the load out of here to here down to there. And not have too much bending because this thing is not going to bend much. Yes?
Here we have vertical springs too for friction.
Yeah, we did. Otherwise, it's going to be unstable, right? Now, you have to, as a designer, sometimes make a bit of a judgment call because in certain soils, your skin friction may be very, very low, and everything just comes from the bearing at the base. It's usually, that's an extreme case. You'll have some skin friction. So we usually have, for each spring, we put in 3 components, 2 horizontals and 1 vertical.
For the horizontal one, you got to use the PY, but for the vertical, you can use the same, right? Because
The vertical, you can also use the same. The vertical also does something quite similar. The soil only gives you so much, and then you can slip relative to it.
but it's not the same length, right?
No, it would be, the 2 horizontal ones would be the same, but the vertical spring is going to be very different. Its stiffness and where it yields and all that is going to be very different. And usually the geotechs will give us those springs. Now, because I'm running a longitudinal pushover, we had to, and we didn't want to have the whole bridge in there because that wasn't going to help us. It was just going to complicate things a little bit. So think about something here. I have this system. And then I have this system. So this system is where my column and my deck are monolithic. In this system, I'm perhaps sitting on bearings. Okay, so let's say I want to run a pushover on a bend for each one of these longitudinally. And I've run my response spectrum analysis and all that. How would you, do you want to run a system pushover on this? So what I want everyone to think about is a local single bend pushover versus a system pushover where you have the whole bridge model. And if you're, say you're tight on time, whether it's research or you're in practice, and you want to get some reasonable numbers, for this case, for running a longitudinal pushover, let's say you know what the delta is for an earthquake level, 475, 2475, whatever. It moves X millimeters. Now you've got to go run the pushover to get your rotations, etc., etc. Would you take the whole bridge, or would you isolate this bend and just run with it? Yeah,
Only the bend.
because there's going to be no real difference. There's no real interaction between this and that. Right? How about this one? I'm assuming the column heights are the same. Would you run the whole bridge, or would you isolate a column?
I think the whole bridge.
Okay, that's part of that answer.
Maybe the abutment would contribute.
No, I'm just saying that the abutments are rollers. I'm just simplifying it. I'm saying let's just leave the abutments alone for a minute.
Okay, consider the PR and consider the rotation of the deck.
Yeah.
So
Yeah.
then you don't need for free, only if
Yeah, exactly. So, what is the deformation here? The deformation profile. It's single curvature.
Single curvature.
Now, of course, there is a shear transfer here, right? Otherwise, it's isolated. So there is a shear transfer. But if it's non-monolithic with just a shear connection, it's in single curvature. This is going in double curvature. So the deck has a stiffness that forces this column into double curvature. So as long as you can somehow account for that rotational restraint from the deck, you can isolate this. How about a third case, which is the same thing, but now the column heights are drastically different? Would you do a pushover with a single bend, or would you have the whole system?
System.
Now you really need to have the whole system, because there is some real interaction happening. You need to figure out which one. This one is obviously going to have the demand concentrations happening. It's going to go first. So you cannot isolate it, because the deck being a rigid diaphragm is going to force both of them to the same displacement. And if you think about yesterday morning and you saw how different the moment curvature and the force displacement graphs were for each one of these individual ones, there is no way to capture that behavior. So in our case, we were sort of like this. So we decided that we were going to take one pier out, but then at each one of the column locations, we introduced a rotational spring to account for the deck. And what you can do is your response spectrum analysis has the whole bridge. You just put a unit load on it, and you get the rotation for that, and then you can just come up with the rotational spring stiffness. Okay, so that's what we did in this case, and that's what this is showing. So all I'm saying is think about these things when you're modeling. Don't overcomplicate your lives when you don't have to. Don't just go in with, I'm going to do this, and then run into some issues. So the response spectrum, yes, but that's a linear analysis. Now with all these nonlinear springs and several bends, if you're running a system pushover, yes, if you're going to get some value out of it, great, do it. This is the time to do it. You cannot avoid it. You have to do it. This, maybe not. Now, if you had, you know, 2 piles and only 10 meters deep with a few springs, you've got the model set up. Maybe you don't need to pull one out, right? So it's a relative effort versus reward thing. Okay, so here is a PY spring input, just showing you that, you know, here is a spring that we're inputting. It's at 1.5 meters, the depth. It's a PY spring. You can put it in U1. So U1, U2, U3. So we had separate springs for each direction. This is just showing you that it goes, it's very stiff initially, and then it goes pretty plastic. So this is not a rigid, this is not a vertical line. It has a certain slope. It's obscured because it happens very early on. So you can see like here, this is happening at about 0.01 units, and then it's at 1.5 units. So there's a large difference. So the figure seems a bit like, oh, it's just rigid plastic kind of thing, which it's not. Then you can put your PM curves just the way we did yesterday. You can also give some post-elastic stiffness, which I talked about a little bit earlier. So here, instead of having a flat line, you can say my moment over your moment for a certain rotation is 5% higher, 10% higher. So this is just fudged. You can play with that. Right? Once you've looked at your moment curvature graph, if you want to be really accurate, you can give it some post-elastic stiffness. Okay, so then you assign your hinges. In this case, we know the hinges are going to happen at the base, and then this is the underside of the cap beam. That's where we've assigned them because this is a new structure. And once you've run the analysis, the longitudinal mechanism, which is hinges top and bottom, 1, 2, 3, 4, 5, 6, all 12 of them, happens at about 175 mils. So this thing becomes a mechanism at 175 mils longitudinally. Transversely, it's a lot more stiff. It happens at about 62 mils. So you can see that this is capturing the behavior fairly nicely. Now for this, if you were to run an overstrength pushover, you'd get the demands in your piles. Then you'd have to make sure that your piles are working. This is the longitudinal pushover curve, as you can see. Now you see this line is going up at a slight slope. It's because I've put in some post-elastic stiffness in my hinges. If I were keeping them flat, then it would form the 12 hinges, then it would be really, really just flat. Now, because I've modeled a bit of post-elastic stiffness into the system, you see a slight slope happening. And that's why I say nominal hinge hardening. I've just modeled that. Same thing here with the transverse pushover. Now I go in and I turn on my P delta. So this is the load case setup. We went through the setup of the load cases for pushover yesterday. It was just nonlinear and we had no geometric nonlinearity. Now I've gone to P delta plus large displacement formulation and I get the same thing. Now I'm at 209 mils. Okay, so it's a softer system. This is the transverse mechanism. And now you see the negative slope to your pushover. Okay, because you're accounting for that, accounting for the P delta effect. Same thing in the transverse direction. Okay, now what I can also do is I can go and put a negative slope to my hinge. So the previous one was capturing your material nonlinearity or your geometric nonlinearity. This one is capturing your material nonlinearity. Should you think like if it's an order structure or whatever, and you You say, okay, well, as soon as it hinges, it's going to start to drop. You can also model some negative stiffness in your hinge. So now I've got, instead of numbers that are above 1, I've got numbers that are sort of below 1. And again, those are just fudge numbers for illustrative purposes. When you do the actual work, you got to look at your moment curvature and you got to come up with those appropriately. And you have to be mindful of what material model you're putting into your software for coming up with the moment curvature graph. Okay.
Are you modifying the material model in this analysis?
No, I'm not. I'm just showing you that if you wanted to model a stiffness degradation, this is where you would do it, if that were the case. This is more for illustration. I'm not modeling.
And you're saying that based on the geometry on the P delta one that you...
Well, the P delta is a separate issue, right? That's large displacement formulation. That negative stiffness is coming from the fact that you've got that P acting.
That's not material.
That's not material. This one is material.
Okay, but...
Yeah, no, so this is going back into the hinge model, right? This is where I was showing you nominal hardening. Now I'm modeling some nominal softening in the hinge. So this is a material issue. The previous one was really just my formulation. I said, please turn on large displacements.
When would you say that P delta large displacement matters? Is there a drift that you...
Not really. No, it will matter if you look at, so a little bit of it is a gut feeling, but the real test would be you turn it on, you turn it off, and you see what the difference is. And if you don't see much of a difference, well, turn it off, right? Yeah. Oh, good questions, good questions. So this again, if you model some hinge degradation, you see that the post-elastic branch is coming down. So the software is modeling things appropriately. And as a result, your plastic rotations might be different when in comparison to the case where you're modeling something that has a positive post-elastic stiffness. Okay. What we ended up doing on this, because we were really pushing the system, and as professional engineers, we weren't really comfortable, quite comfortable with the system. On these columns, what we proposed was to wrap them anyways with fiber. Even though it was a new structure, when we did our independent review, we gave them this suggestion or recommendation that this needed to be wrapped. We were a little bit worried about having shear failure and confinement failure, even though these things were confined really, really well. But the diameter of the columns were like, I think it was 400 or something. It's a real slender column. And so what the one of the solutions we came up with was to just make sure that the cover would never fall off these things. So on the new structure, and there was some resistance, but then we were able to show them, and we were able to say to them, look, this is good insurance. You don't want your structure in an earthquake to sustain too much damage, because when the cover goes, the core is just, there isn't a big column, and you spall 70 mils of cover or 60 mils of cover on each side, and you still have a meter left. This wasn't the case here. You were losing 30-40% of your section, and we just didn't feel comfortable doing that. And that's something that happens in practice. Is a lot of the times you try to add in some extra insurance, making sure that you're not driving the cost up by a lot, but you don't turn it into a large project and study to death. You've got to come up with a practical solution which is cost effective and move on with life.
Sorry, basically where does this hinge degradation come from?
So physically, the hinge degradation comes from several things. The one thing is when you pull on the one side, your rebar yields. Okay, when you reverse it, that rebar has now lengthened, and it has a tendency to buckle under the reverse cyclical loading, but now it's under compression. So I was looking at some specimens yesterday outside in the lab, and you see on some of those smaller columns, not the one that Sharif tested, you had real good shear reinforcement in them, you can see the rebar has buckled. So once the rebar buckles, you see that this thing starts to go down. Now, when you do this subsequently, low cycle fatigue also kicks in. So under low cycle fatigue, you have high amplitudes, but you have fewer cycles. Usually when we think about fatigue for materials, we're talking about low amplitude, high cycle fatigue. But seismic events, they induce high amplitude, low cycle fatigue in them. So now if you were to take a rebar and you were to do a monotonic test on it, it might rupture at 0.09. Now if you go back and forth, it might actually rupture at 0.04, 0.05. So the next thing that happens is after a few cycles, after things have buckled, then now you can start to have rebar rupture happening. So now you're starting to lose your rebar. Not all the rebar is lost, but some of the bars are going to break. So of course your structure is now even less stiff and less strong. That's more, so the degradation has, the third thing is you get strain penetration going into your element underneath, and you have bond slip in your rebar. So all these mechanisms give rise to degradation. Those are harder to capture in a lump plasticity model, right? So you have to like fudge things based on your experience and your, yeah.
I'm thinking when we're doing fiber models, I never do this. We always
Yeah,
and it goes up.
it's because your material models, you're not using the material models that capture those. So if you were to use Monty-Newty model or those that actually account for the Bauschinger effect, they account for buckling. I've recently started looking into it. There is Professor Kashani, I think, out of Bristol in the UK, and he's come up with a really nice model, and it captures the different effects. And he's using fiber models. He's using open Cs. So there's a fatigue model in there, and then he's come up with his own model with the strain penetration with a zero length element, and you see this thing happening all over the place. So yeah, if you use a model which doesn't capture all of this, of course you're not going to see it. But if your model should be able to capture it.
Yes, so the only thing now is that is for when we go into that situation. Before that, we still have the post-plastic going up, right?
Yeah.
So those things come into the resources. So
Yes. 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 Yes.
But if we define this like this from
Yeah.
the beginning, you will go like
Yes.
this.
So that's a very good point. That's a thing about the analysis that we're doing. We cannot account for all of that in a static analysis. We can only account for that in a true nonlinear time history analysis, which captures the time component and all of that. So this is really just coming up with your worst case scenario and trying to bound the problem using a simpler analysis tool, which is a pushover analysis. You're exactly right. Those things, that's the limitation on the analytical, the analysis method. It can't capture that. But that's not to say that you should jump straight to a nonlinear time history. You need to first understand. Well, I think my hinges are going to form here. Are they going to form there? Now, when I match my response spectrum target, am I far enough that any of those effects are going to be kicking in? If my steel rebar is sitting at 0.015, I'm going to be wasting my time coming up with all those, really high-end material models. And what am I going to gain out of it? So go step by step. Do your response spectrum, do your pushover, understand your load path, understand how your structure is likely to behave, and then you have to make a decision whether there is value in nonlinear time history or not. And even within the nonlinear time history, are you just going to use a simple model to demonstrate, if it's a lifeline bridge, you have to do it. But from this pushover and the response spectrum, we find that it's only going nominally into the inelastic range. None of those effects are going to kick in. So why am I going to put in very sophisticated models when I'm not going to be using those? Those things need to be thought about, because it's a lot about effort and understanding. You can put in stuff into your nonlinear time history analysis and you can get reams and reams of data, but you have to make sense out of it. And it can be complete garbage if you don't understand what you're doing. Okay, so that's just showing some of that. Our code has has a couple of lines in there that says you have to be able to take 50% of your live load post your earthquake. So one way of kind of looking at it is you put your live load on there, live plus dead load, and then run the pushover. Okay, so assume that all that traffic is sitting up there when the earthquake hits. But this is only capturing the gravity effect of that load. As I was saying yesterday, we don't account for the inertial effect of that load. So far, I haven't. Well, when we do our, I've been involved with a couple of projects where we were designing transit lines, and we had to take the live load effect of the train sitting on the line. And in one case, I think we were asked to take 50% or whatever of it and also account for it as an inertial load. Usually that is a pretty small percentage of the mass of the structure, so it doesn't add a whole lot, but it is meaningful to add it from a gravity point of view. So one way of doing this is to put your whole dead plus live load on there and then run the analysis. So we know this from yesterday. You start from your dead load stressed case and you run a nonlinear analysis and you get something like that. Now, what I did was I set it up differently. Okay, running the pushover from that stress state. Anyone guess what would happen? It doesn't converge. It didn't converge. Can anyone think of a reason? Yeah. Yes, so that's exactly right. It's already, now this is a vertical load that you're applying on it and it's unidirectional. It doesn't go back and forth. So you've already formed a mechanism. And now if you want to put some load on it, how is it going to be able to take it? It's not going to be able to take it. So one way of doing this is to give a pretty high post-elastic stiffness to your hinges and then run it and see what happens. Well, you cannot artificially give it an artificial stiffness. You just have to give it enough to kind of run it. The issue is that after the earthquake disappears, those bending moments that are happening when it's plastic are also going to go away. So it's going to retract to a certain point. Okay, so I think the best way to do this is to figure out what residual deformation is going to be there in your bend. And then pick that state, and hopefully by then all four hinges they're not back to zero. They'll have some locked in moment because it'll be sitting kind of like this. Now put your live load on it, and then you will get an answer. So you can capture that in that scenario. The only issue is to get your residual drift, you need to run a pushover analysis, or sorry, a time history analysis. Because otherwise you don't know, after the earthquake is gone, where is it going to be sitting? How far back is it going to come? Okay, I haven't thought of a way of coming up with, yeah, that's, I'm just gonna assume, or maybe you assume, 0.5% drift or something and see, okay, if it's got 0.5% drift, it still is able to take it and find that bound. Well, there's a thought that just came to my head. You can look at it in different states and kind of see where, how far you can push it and then put the live load on it for it to be able to take it. And now you can, as part of your drawings, you can say, well, somebody needs to go there and look at what residual drift is there after the earthquake before they put traffic on it. Okay. The other thing one could do is say, okay, well, I've got 50% of moment locked in, or 70% of the moment locked in. Can I take this or not? So you can make some guesses, but if you really want to do it in a thorough fashion, in a deep fashion, then you need to run the time history analysis, let it stop, run it for 20, 30 seconds just so that it damps out and now it comes to a true equilibrium, whatever that residual state is, and then you put the live load on it from that stress state. Okay. This is something we talked about yesterday. This is your baseline curve. Don't use this to design your your capacity protected elements and don't use it to safeguard against brittle failure modes such as shear and all that. This is something that I pulled out of this is notional because it was on an actual project which I can't really talk too much about, but we did a seismic retrofit on a big bridge in Vancouver. What we found was this was the plastic hinging sequence. So 1, 2, 3 at the bottom of the 3 columns, 4 and 6 at the top of the 2 columns, the left one and the middle one, and the 5th one happened in the cap beam. Okay, so that's how the 6 hinges formed, and then it became really flat. And this was our ultimate if we went all the way to the failure in the critical hinge, like flexural failure, running out of flexural ductility, where you're hitting your strain value of 0.06 or 100% of your core crushing strain. And the issue was the column shear kicked in right here. The joint shear kicked in right here, so the joint failed over there. This was our 1 in 475 demand, and this was our 1 in 975 demand. So the pushover is not going to capture your brittle failure modes on its own. The pushover has no way of figuring that out. Pushover assumes that you've got that ductility and it will only stop when you tell it to stop. It's up to you. But outside of that, you do your calculation for column shear and you say, well, that's only getting up to this base shear. Sorry, my joint shear. And then over here, my beam is going. So just past this, so this number 5 forms, and then the beam hinge just completely fails. Okay, so then you have to, this is a fictitious point then. This point would only be valid if all those failure modes have been suppressed. So now you go and you do beam strengthening, and you make sure that your joints, so we ended up putting fillets on the joints. So basically make the joint size larger, we put in more rebar. So the joints were like this. We went in and we filleted it, and we put some rebar through. And then we also did some fiber wrapping of the column. Once you do all of that, now you've got this much capacity. Okay? So don't think that the pushover is going to give you all the answers. The pushover is a brilliant tool. Once you start to superimpose all this other information, you can really start to develop a picture of the performance and the behavior of your structure.
Do you have the detailing of that bed?
I can try and find it. Yeah.
That would be good.
Yeah.
Good case study.
Yeah. Yeah. It's been retrofitted. It's a Knight Street Bridge.
Okay.
I'll have to go dig. I was involved with it back in 2004.
Okay.
Several people here weren't born at that point.
So maybe we can work on this. It will be interesting. So.
Yeah. Yes, sir.
So after that, do we have to perform the pushover once more to see the performance?
Yes, you may or you may not. If you haven't changed the stiffness of your structure, like if you've just got fiber wrapping done. Yes, this is going to stiffen up your structure, so you have to rerun it. You have to have a local element that's giving you a little bit of a higher stiffness, and then just make sure that everything is working still fine. Yes.
The shear failure models to model the model and then
The shear failure models. Very difficult to have a shear failure model for bridges that were done in the past and you don't really know how they're going to behave. So what you do is you come up with a very conservative lower bound shear capacity because you just have no trust in the model. You just cannot trust the science too much because these are so badly detailed. There's so many things that can go wrong that you just keep your bare minimum, and as soon as it hits it, because people's lives are dependent on it, right? So now the decision becomes easy. You've got to go retrofit it. Right? So this is one of the spins I've put on the 90% and 80% of capacity retention. And this is now drawn much better. It's part of the, I got it into the BC design of bridges, the performance-based design of bridges guidelines that.
From the CCE, they were handing this guideline.
Oh, they were?
Yeah.
Oh, really?
But
Okay.
I forwarded to all of
No, it's a hard copy, doctor, I guess.
no, like there's
It's a soft copy on the internet. I think everybody should have that if you're doing bridge design. It took us about 2 years to do it. Actually, it started with at the CCE in 2015 in Victoria when Charlie Huffman, who's the chief bridge engineer, she came to me and she said, "Well, I have something for you." I said, "Yes, ma'am. What can I do?" So we put together a committee of people that helped. I was the lead author on it, but then I had lots of help from lots of people, graduate students, and also some very esteemed people from the industry. And as part of the EGBC process, we also had to have a committee, a larger committee from within the practicing community that got into a lot of discussions with us. We weren't bound to take all of their advice, but they were there to keep us on track and give us comments. And I think we incorporated most of their comments. Ultimately, we are the authors, we took responsibility for it, but I think that whole industry collaboration was quite good, so it came together quite nicely. And until something else comes along, which hopefully in the next 3-4 years I'll have some handle on, I said, well, the idea is, and I've read a lot of papers by then, because when I was in the code, I've been in the code committee, and we've been talking about aftershocks and degradation and all that. And so in 2016, I started thinking about this. So what usually happens with aftershocks is they start to damage your structure once you're on this degraded path. If you're getting your your aftershocks and you're still on the positive slope, you're still on the ascending branch, it's not that big a deal. But once you start to degrade, now things start to develop a bias and rebar buckling happens, blah, 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 it becomes a bit of an issue. And I spoke to the people and they said, well, we came up with this just to make sure that you're not designing to that point. That there is some reserve in the system in case there's an aftershock. So there wasn't a whole lot of thought put into it, but there was some basic thought put into it. So the code basically says for repairable damage, you have to retain 90% of your capacity to make sure that aftershocks won't bring your structure down.
And again, sorry, the capacity of what? The force of the
Yeah, I'll talk about that. So then the other thing is 80% capacity retention for extensive damage. And that's a very valid question. What capacity? Force capacity, displacement capacity? What are you going to do? And I know that on the practice side of things, we're not doing a whole lot of nonlinear time history analysis, at least on major route bridges and other bridges. For lifeline bridges, yes, that is mandatory. So we came up with this formulation and we said, okay, well, you do a pushover, have some measure of degradation in your hinges, and where appropriate, you have to account for your P delta effects. So then this is my full capacity, my peak capacity. This is 90% of that, and this is 80% of that. And I've got displacements relative to those. Okay? So these become my performance points. My displacement cannot be larger than these, not larger than this for repairable damage and not larger than this for extensive damage. So now it becomes a double, like a check where you have to check against this and you have to check against the rebar ratios, because those rebar ratios will also give you two different points. The rebar ratios, I think, for minimal damage are so low that you're not going to be on the degradation path anyways. Okay? When you're pushing into extensive damage and you're going to 0.05, you may be on the descent. You may be going down. So then you might want to incorporate that in your pushover and make sure that both criteria are satisfied. So whether 0.05 happens first or this reduction happens before then. So your displacement capacity is going to be based on whether you hit the strain limit or you hit the degradation point. Okay, so that for now is a very simple sort of way of thinking about it, and we've said that's what we're gonna stick with.
So this comes down very much is dependent on when we define the material.
Yeah.
The concrete.
Concrete and steel. Yeah.
So concrete, we don't have that many like models to say, okay, it goes down to here.
Yeah.
Or
It's not going to be primarily driven by concrete if your core is confined very nicely, because your concrete core, if it's confined nicely, it keeps giving more. It's more of a rebar issue.
But still the confined concrete goes down. Like,
Yeah, way out there. Yeah. So you have to have that in there. So when you run your moment curvature analysis, you got to see what's going on, right? So one way of coming up with that negative stiffness is to see if your moment curvature, when you run the whole way, it does this, right? So then you have to make sure that maybe you trilinearize it, okay? And then you can also have a double or triple slope to your plastic hinge in there, because it gives you 3-4 different points. So you can also have it go up for a certain portion and then have to start it come down. So you can model that. Okay, I think we're at 11:15, so we've been going for 1 hour and 45 minutes. And now I'm gonna transition into the nonlinear time history analysis. So maybe I'll open the floor for a couple of minutes if there are any questions. And other than that, maybe we'll take a 10-minute break, let people just decompress a little bit. And yeah, any questions? I mean, it's good we've been having questions, but any questions? Yes?
I have a general question regarding the bends, like if it's a single bench beer or a double bend or more or multiple bends. When do you take the decision to change the bend? Is it like the geometry, the space, or maybe during the pushover or whatever analysis you are doing, sometimes you change the bend?
So usually it happens early on. So if your bridge is 15 meters wide, a single column is going to have a pier cap, which is cantilevering out 7-8 meters. That's going to make your pier cap very, very deep. Okay, so if your bridge is 6, 7, 8 meters wide and you have a 3 to 4 meter overhang, you're probably going to go with a single hammerhead pier. Okay, but when you're starting to get wider than that, when you're hitting 10 meters, 15 meters, there is no way that you're going to keep just a single column. Now, let's say that you have to put a bend and you've got traffic lanes there. So now it's got to be a straddle bend. It's got to have 2 columns, one in this zone, in this median maybe, and one all the way across. Now, you may be looking at a 20-meter span. So now your columns are going to get big, your cap beam is going to get big. You might even have to pre-stress your cap beam, and we have to do a lot of that at times when we're going across lanes. So it's a lot of the times it's the geometry of the bridge that drives that. And then, as I was saying yesterday, if you keep your axial load ratio for dead load around 10 to 15%, your number of columns is going to be reasonable. But then again, if you're getting 4 for those, but you can't put 2 in between, then you maybe go with bigger columns and you gotta go wider. So it's load and it's geometry. It's if you've thought about it right, and that's conceptual design is a very different animal when you're thinking of it, right? At SCABC, we do a conceptual design course. I just did that in early this year. I have 2 other people, and the whole idea is that we give you we deliver lectures, but then it's interactive workshops. So we come up with open-ended problems. It's kind of like the I-Struct-E exam, where it says, here is your site, these are your constraints, you got to go from point A to point B, this is what the soil profile looks like, you can't put any columns here because there's a rail line or there's a river. Think about, just conceptualize it, no design of the elements. Would you do a girder bridge? Would you do a cable stayed bridge? How many spans? Like, how deep are the girders, do you think, are going to be? So that just, there is no book to teach that. You just learn it through experience. But these rules of thumb kind of come in quite handy.
I have another question regarding, I know, like, generally speaking, when the code says the strain in concrete, the strain in steel, it knows that we are using the common steel reinforcement, the common concrete. When it comes that if there is a different, for example, grade of concrete in the same bridge, or we are applying different type of concrete, for applying RCA in bridge, it might be not a practical point of view, but if in a research point of view, we are doing that. Applying stainless steel instead of steel, high strength steel instead of regular steel, FRP.
Yes.
So how can we try to uptake whatever is applicable from the code in terms of performance levels? Because when you say strain of, for example, of value, it does not apply for FRP.
Yes. That's a very good question. And if you look at the code, there also, you find some qualitative descriptions of damage and performance. So these strains for general materials have been tied to those, but there are qualitative descriptions. So I think we all understand what minimal damage means. Like minimal for us would mean, you know, you really don't have to do much, or you do a little bit of grout injection and there are no permanent offsets. The thing is standing plumb and all that. So if whatever material you're using and with your models, you can show that, you know, you're there. And we all kind of understand what extensive damage might be. Okay, it might mean the cover has completely fallen off. It might mean you've got some buckling of the rebar, some extensive yielding of the rebar. So whatever rebar or concrete you're using with your materials, you can define your strains, or you can, as long as you're meeting that performance. Extensive damage or repairable damage, can you repair it in a month? Is sort of a guideline for the code, from the code. Can you repair this damage within a month? If you need to have one lane open to traffic for ambulances and fire trucks, is your bridge going to be leaning over so far that you have such misalignment that you can't? So you can take all of those, the philosophical side of the code, which everybody understands because it's more physically meaningful, and you can use those to then calibrate things. That's how I would do it, because the code does set the framework for it. And this is again a lot of there is a lot of discussion happening amongst ourselves within the code committee, and there is a group that says you're putting these strain limits. What if somebody has a different material? Well, what if somebody is using completely different? And the answer to that, and we've said, well, if you do force-based design, you just have no way of doing it. With performance-based design and these performance levels and criteria and damage descriptions, you've at least got something. You're giving the designer the tools. Now it's up to the designer to show that you're meeting that, right? So performance-based design's beauty is that it gives you the framework. And it's less about strains and all of that. Like, yeah, we go there, but you could also cast the same thing in terms of rotations or deformations or whatever. As long as you can show with some measure of confidence that you're meeting the performance, you can use material from space. That's what performance-based design opens it up to. Anyone else? Well, let's take 10 minutes. It's 10 to 11. Let's be here at 11. Let's start, otherwise we're going to go on forever. I've got a fair bit to cover still.